In this video, we are going to go over different types of problems that can be modeled using rational equations. So the first type that we've got cost problems. We also have distance problems, work problems, and mixture problems. We're going to get started with a cost problem right here. Ramona is trying to decide between two satellite internet providers. ProSat Internet charges a $250 installation fee and a monthly fee of $50. SuperSat Internet charges a $90 installation fee and a monthly fee of $58. Determine when the average monthly cost, including installation and monthly fees of each service, would be the same for both providers. So let's start with provider one, ProSat. ProSat has a $250 installation fee and then a monthly fee of $50. So if I was going to write an equation, we're looking at the average monthly cost for each of the providers. So if I want to write an equation for the average monthly cost for ProSat, it would be $250, which is the installation fee, plus 50 times X, because X would represent the number of months. So you pay $50 every month. And then we divide that value by X. So 250 plus 50X, that's how much you pay for all of the months total. And then we divide by X to find the average per month. We'll also do the same for SuperSat. SuperSat charges a $90 installation fee and a monthly fee of $58. So their equation would be 90 plus 58x divided by x. And now this problem is asking us to find when the average monthly cost for each will be the same. So that means we're going to set these two equal. Well, if I set these two equations equal, now I just have a rational equation that I can solve using some of the methods we've learned. When we like to solve these, one of the ways that we can do that is by looking for common denominators. And actually in this problem, we already have them. When you have common denominators, then you can just set the numerators equal. You can ignore the denominators. So we will get 250 plus 5x equals, sorry, not 5x, 50x equals 90 plus 58x. And we can ignore the denominators because they are equal. From here, I'm going to solve for x. So I'll subtract 50x over from both sides. That way it cancels here. And then I'll also subtract 90 over to the other side. So that way it cancels here. And we get 160 equals 8x. Next, I'm going to divide both sides by 8, and we get x equals 20. So our final answer then would be after 20 months. So we can put that, they will be the same. After 20 months. With application problems, we always want to respond to the context of the problem. And there you go, that's an example of a cost problem. The next type of problem that we're going to do is a distance problem. Mary spent the first 120 miles of her road trip in traffic. When the traffic cleared, she was able to drive twice as fast for the remaining 300 miles. If the total trip took 9 hours, then how fast was she moving in traffic? For problems like this, it's super helpful to write a table because then in your table, you can organize the different pieces of information and figure out where our equation is going to come from. So there's one already here for you. We have both traffic and no traffic. And we know that the distance that she traveled in traffic was 120 miles. And the distance she traveled without traffic was 300 miles. The next column is her rate. For rate, we know that she got to drive twice as fast when there was no traffic. So we don't know her speed. We do know that the speed without traffic was 2 times the speed with traffic. And so that's where we get x and 2x from. The last column is time. Now, I don't know how much time she spent in traffic versus not in traffic, but I do know that the total amount of time that she spent was 9 hours. Looking at this table, in order to use the information we're given to solve, we are going to need the time that she spent in traffic and no traffic. Even though we don't know the exact time, we're going to use the distance equation to fill in that column. So if you remember, distance equals rate times time, and I know that that's written up above for you. And if we want to find time when we have distance and rate, we would just divide both sides by r, and we get that time is equal to distance over rate. And that's how we're going to fill in this time column. We're going to take the distance that she traveled, 120 for traffic, and divide it by the rate that she was traveling at. And then we're going to take the distance that she traveled without traffic and divide it by the rate that she was traveling at. Now, the reason that we need to know the time for both of the traffic and no traffic is because time is the only thing I know a total for. So that's what's going to allow us to set up our equation. So if she spent 120 over x in traffic, so 120 over x, and then she spent 300 over 2x not in traffic, if I add those together, that would be her total time, which we know is 9 hours. And putting that together, now we have our equation that we can use to solve this. In order to solve, I'm going to work on getting common denominators. So for the first fraction, it has a denominator of x, and the second one has a denominator of 2x. So the first one is going to need a 2 in order to be 2x. So we have this, and it's equal to 9. We can think of this as 9 over 1. So we'll have to multiply 9 over 1 by 2x, since it didn't have either the 2 or the x. Now all of the denominators are the same, so I can just take the numerators. 2 times 120 plus 300 equals 9 times 2x. And we are going to go ahead and solve. So 2 times 120 is 240. And 9 times 2x is 18x. 240 plus 300, that's 540, equals 18x. Divide both sides by 18, and we get x equals 30. So what does that mean? In traffic, she was going 30 miles per hour. And when she wasn't in traffic, she was going 60. All right, we're going to move on to a work problem. This is another problem where a table is super helpful. Anita and Martin are the assistant managers for the marketing department of a pro hockey team. They need to mount ads to the rink boards before the season begins. It takes a team of 3 people to attach each ad. In past seasons, Anita's team attached all the ads in 20 hours, and Martin's team attached all the ads in 30 hours. This season, Anita's and Martin's boss asks them to have their teams work together to get the job done faster. And the question that we want to answer is, how long will it take them if their teams work together? So if you want to put that in there so you know, how long will it take both teams? So we're going to start by filling in this table with the information that we were given in the problem. One thing that I see here, we know that Anita's team took 20 hours to complete this job, whereas Martin's team took 30 hours to complete this job. So what we have in the first column is work rate. We need to figure out the work rate for Anita's team and Martin's team. To do this, think about it kind of like almost like a proportion. They both did the same one job. How long did it take Anita's team to do the one job? It took them 20 hours. So for one job, they spent 20 hours. That is Anita's team's work rate. For Martin's team to do that same one job, they took 30 hours. So that right there is their work rate. Now we want to figure out the portion of job that was completed by each of them when we put them together. So the reason that time is X in this scenario, where you might have thought it was 20 and 30, is because now we're talking about them together as a team. How much time did they spend? And we don't know how much time they spent when they actually worked together. And that's what we need to solve for. But what I do know is that out of the time spent, Anita's team works at a rate of 1/20. So if we want to consider the proportion of job that she completed, all we have to do is do work rate times the time that was spent on the job total. So we do 120 times X and we get X over 20. For Martin, his team can finish the job in 1/30. That's their work rate. And then if we can do that work rate times the time it takes for both teams to complete the job, we get X over 30. The reason that this is important, what portion of the job can they complete, is because what I know is that together they have completed one job total. So to set up an equation for this scenario, we know that Anita's portion of the job she completed plus Martin's team's portion of the job that they completed is going to be equal to one completed job. From here, we want to go ahead and get common denominators and solve for X. For 20 and 30, the least common multiple of them would be 60. I can get 20 to become 60 by multiplying by 3. And then 30 to 60 by multiplying by 2. And then I can just make this one 60 over 60. So now they'll all have a denominator of 60. We get 3x over 60 plus 2x over 60 equals 60 over 60. Now that the denominators are the same, we can ignore the denominators and just set the numerators equal. We've got 3x plus 2x, which is 5x, equals 60. Divide both sides by 5, and we get x equals 12. So as a team, it will take 12 hours. Last, we have a mixture problem. Manuel spends time in the chemistry lab for his class. He is conducting an experiment for which he needs a 2% salt solution. However, all he can find in the lab is 120 milliliters of 10% salt solution. Part A says, how many milliliters of salt and how many milliliters of water are in 120 milliliters of 10% salt solution? Well, if in 120 milliliters, 10% is salt, we can do 120 times 0.10, and that will give us 10% of 120, which tells me that there are 12 milliliters of salt. Now, this solution is just made up of salt and water. So if 10% of the solution is salt, that means 90% is water. So we can do 120 times 0.90, and that's equal to 108 milliliters. So we have 108 milliliters of water. Part B says, what is the concentration of the salt solution when Manuel adds 80 milliliters of water? So if he were to take this solution and add 80 milliliters of water, what would then be the concentration? So the concentration is calculated by taking the amount of salt and dividing it by the total mixture. So we would do 12 over 120. That's what told us that this was a 10% salt solution. But if he adds 80 additional milliliters of water, then we're adding 80 milliliters to the solution. But he's not adding any salt, so we don't add anything to the numerator. When we combine this, we get 12 over 200. This is equal to 0.06, so it's now a 6% concentration. Part C says, write and solve an equation to calculate the amount of water Manuel needs to add to the 120 milliliters of 10% salt solution to make a 2% salt solution. Let X represent the amount of water Manuel needs to add. So similar to B, we're starting out with our 10% solution. He has 120 milliliters of that solution, which means there's 12 milliliters of water. He needs to add water to dilute the solution. So he wants to add water, but not add any salt. So he's going to be adding milliliters of water. And we add that to the denominator. His goal is to get the 2% solution because that's what he needs. So we're going to set this equal to 0.02, and now we're going to solve. When I go to solve this problem, I'm going to start by multiplying both sides by 120 plus x. Because those will cancel. All right, so we are going to now distribute 0.02 to the 120 plus x. So we get 2.4 plus 0.02x is equal to 12. Now I'm going to solve this. We will subtract 2.4 from both sides. And I get 9.6 equals 0.02x. Then I'll divide 9.6 by 0.02, and I get 480 equals x. Therefore, he needs to add 480 milliliters of water.